Hi class, welcome to the first lecture of linear algebra for this term. We're going to start with something easy just to get ourselves used to the language of linear algebra. The basic components that we need to work in linear algebra are vectors. Now I know some of you have seen vectors in high school. In fact, maybe all of you have seen vectors in high school. We're going to go through a brief introduction of how I would like you to think about vectors in the context of linear algebra, which is a more general context of however you've seen vectors before. Now, let's start with something easy. We're going to start with two-dimensional vectors. That's vectors with two components, and then we'll go to vectors with three components, and then generalize to n components, so an arbitrary number of components. Here's a column vector, a typical column vector. V with components V1 and V2. So we will refer to V1 as the first component, of V, and V2 is the second component. Where V1 and V2 are in fact some numbers. So, example, V could be the vector 2, 3, or V could be, let's say W, another vector, could be minus 3.5 and 0.5. There could be many different numbers. You could have another vector, say U equal to pi and E. These numbers that many people don't really like, that come from calculus. We're not going to need pi and E, so do not worry about that. So different examples of vectors that have two components. What could these vectors represent? Well, let's say you have a farm and your farm produces apples and oranges, and you'd like to keep track of your apples and oranges. Well, you could allow the first component V1 to stand for apples and V2 to stand for oranges. So now your vector V represents the fruit yield of your farm, for example. Now, there are two operations that we're going to want to work with when it comes to vectors. The first one is easy, it's addition. The only requirement so we can carry out addition is that the two vectors have the same number of components. So if I have a vector V with components V1, V2, and a vector W with components W1, W2, then addition is carried out component-wise. It would be V1 plus W1, V2 plus W2. And in the context of apples and oranges, this makes sense. If the first components are the apples of, say, two farms, then, the joint farm has V1 plus W1 apples and V2 plus W2 oranges. So this is addition of two vectors. The other operation is scalar multiplication. Now, scalar here means a number. So this is just some number. Any real number would do. So scalar multiplication is something of the sort, generally speaking, it would be C times V equal to CV1, CV2. So although things kind of look the same, this is a number and this is a vector. So the vector would have two components, the number has one component. And it is important here to know that this is compatible with addition in the following way. So if I chose C to be a 2, I want to think of 2V as V plus V. it's sort of the way we think of multiplying by numbers when we have unknown things, when we have variables. When we say 2x, we mean x plus x, or we mean 2x's. If we have, for example, 5y, we mean 5y's. We mean y plus y plus y plus y plus y. Five of them. We have that same way of thinking with vectors, because as you know, as we've seen from the way we defined addition, v plus v would be v1 v2 plus v1 v2. You add them component wise, you get v1 plus v1, v2 plus v2. Well, v1 plus v2 is definitely 2v1, v2 plus v2 is 2v2. So we see that the definition of scalar multiplication, as done over here, is the same as, sort of is consistent with scalar multiplication of each component in the vector. Okay, let's look at some examples with numbers. I know letters can be a little scary. So, for example, if let's stick with v being equal to the vector 1, 1, and w being the vector 2, 3, then v plus w, for example, would be 1, 1 plus 2, 3. Their sum would be another vector with components 3, 4. Okay. Now we can combine addition and multiplication to get something more interesting. So let me say here a linear combination of v and w. So how do we define a linear combination? Well, a linear combination of v and w would be an expression of the sort cv plus dw is a linear combination of v and w, where c and d are some numbers or scalars. So you see here, CV represents scalar multiplication, dw represents scalar multiplication, and the two are combined by addition. So we know exactly what to do when we have CV plus dw. For the examples that we have for our v and w, CV plus dw would look like that. C times the vector 1, 1 plus d times the vector 2, 3. Scalar multiplication here would give us the vector cc. Scalar multiplication with d times 2, 3 is 2d, 3d. And when we add the two component by component, we get c plus 2d, c plus 3d. So we see that all combinations of v and d look like that. Their first and second components are precisely defined. So as long as you have a vector that looks like that, you're good to go. Let's look at some examples. So how do we get different combinations, different linear combinations of v and w? Well, we just need to pick some c and d. So if we take c to be 1 and d to be -1, what do we get? Well, we simply get v minus w. So we see that subtraction is in fact covered by linear combinations. I don't have to define it, in a special way. I don't have to say we have addition and we have subtraction. subtraction actually comes from addition and scalar multiplication. So we would have 1, 1 minus 2, 3, and we know that this needs to be carried out component-wise. So we would have -1, -2. So we see that subtraction is in fact a linear combination. Another typical example of a linear combination would be if we were to choose C to be 0 and D to be 0, then we would get 0v plus 0w. We know that that's going to be the 0 vector. So this is a vector with component 0, 0. And in this way, we see that we can get many different vectors if we look at linear combinations of v and w. Now, what is interesting to ask is, what do we get when we look at all linear combinations of v and w? Then to answer that question, we have to go into different representations of a vector v. So ways to represent v. Well, obviously we have two numbers. So the first way is the way we have it, v equal to v1, v2. So using two numbers. Or in other words, we can represent v through its components v1 and v2. Another way to represent v is an arrow from 0, 0, so from the origin. So we can represent it on the Cartesian plane. And the third way would be just a point in the plane. And by that point, we mean the point v1, v2. So let's look at these graphically. And I'll use the example v equal to 4, 2. So obviously, just by writing v equal 4, 2, that's the first representation. The second representation would be an arrow, and the third would be at the point in the plane. So the point would correspond to 4. So we have 1, 2, 3, 4 in the horizontal axis, and we have 1, 2 in the vertical axis. Then the point 4, 2 is right here. So this is the point 4, 2. Now what about then the arrow? Would be this one. The nice thing about the arrow representation is that it has direction, it has length, and these are things that you have most likely seen in high school. You have seen the vector represented as an arrow. Now, what if we want to add two vectors? So let's say we take the vector w to be -1, 2, for example. Let's represent -1, 2 as well. So I would need here -1 and 2. So the second point would be right here. So this is v. Then w would be -1, 2. It would correspond to the point -1, 2. And as an arrow, it is right here. So here are two vectors. Starting at the origin, that's arrow from the origin. Now, how could we represent their addition? Hopefully you have seen this in high school. The addition would be, if I were to sort of map, so this is v and this is w. If I were to copy V but starting at the end point of W, and then copy W starting at the end point of V, they'll meet at some point. That point will be V plus W. So the arrow that corresponds to the sum would be the diagonal of the parallelogram. So this is V plus W. And this is something typical that you would likely have seen in high school. Now, why is this important? Why is this interesting? It gives us a little bit of intuition about the things that vectors could potentially represent. Now, when I ask the question, what is the space of all, this is very important, all linear combinations of V and W, the same V and W in the example, then what we are starting to think about is what are all the different points that we would get, or the different vectors that we would get. So when we talk about this space, imagine it consists of this point and that point and that point. Can we produce another point? Well, sure. So this point over here, this vector corresponded to V plus W. Remember, linear combinations are expressions of the form CV plus DW. So when we took V plus W, in fact, we took C and D to both be equal to 1. Well, we could look at, so we could take a choice C to equal 0 and D to equal 0. So if both C and D are equal to 0, then CV plus DW would be 0. So we see that 0 must be in that space. We could take C to equal 1/2, for example, D to equal 0. What does that give us? Well, that gives us this point over here. It's a half of V, right? Well, what if we took C to be 3/4? Well, then we would take that point. We could take 1/4. In fact, we see that we can take any point on the line that passes through V. What happens if we take C to be 0 and D to change from negative infinity to infinity? So I don't know, this could be -1, for example. That would be that point there on the line that passes through W. So by setting one of the scalars to 0 and letting the other one change, we're describing lines through the vector V and the line through the vector W. And then you see that any combination, now these can be used again as points, any combination would also be there, right? All of these points would correspond, and we could have points here and here, and then we could have points here, and they would correspond to different C's and D's. So in fact, the space described by all linear combinations of these particular two vectors is the whole 2D space. So all linear combinations of the form C times 4, 2 plus D times -1, 2 describe the entire plane. All right. Now, what about, would this always be true? This is an important question. If we have two vectors, are we always going to get a plane? Usually, yes, but not always. So what are some examples when we don't get the entire 2D space? So let's look at such examples. If V is the 0 vector, and if W is the zero vector, then all combinations C times 0, 0 plus D times 0, 0 will look like 0, 0. So here the space is just the origin, 0, 0, right? That's all we can describe. Another example could be of the following kind. We could have V to be, for example, 1, 0, and W to be negative 1, 0. Then C times 1, 0 plus D times negative 1, 0 look like this. C minus D, 0. What is interesting here is that the vector V has the first component non-zero, the second component 0. The vector W is in the same way. It has the first component negative 1, but the second component is 0. So then when we look at their linear combination, the second component has to be 0 because you cannot produce something non-zero from a 0. So what is the space then described here? Well, let's draw this. This is important to visualize. So the vector V corresponds to 1, 0. So that's that point here. And the vector W corresponds to negative 1, 0. So that's over here. Then any combination of the two will have to stay on that line between them. So if you have the one vector and you have the other vector, no matter how you add them, you're going to be on that line. So in fact, anytime two vectors are on the same line, their linear combination, the space of all linear combinations of those two vectors will have to be that line. So here what we get is that the space is a line through the origin. This is important. The origin will always be in the space of all linear combinations. Why is that? Because when you look at the expression CV plus DW, you can always choose C and D to be 0. So no matter the answer, whether you get a line or you get the 2D space or you get the 1D space, the 1D space actually is the origin. So you could either get the origin, you could get a line, or you can get the entire 2D space when you're working with 2D vectors. The situation is very, very similar when you work with 3D vectors. So I'll go through this very briefly. When we have three-dimensional vectors, let's say you have a vector V with components V1, V2, V3. You have a vector W with components W1, W2, W3, and a vector U with components U1, U2, U3. Addition is component-wise, just like in the 2D case. Scalar multiplication is component-wise, just like in the 2D case. And so what do linear combinations look like in here? Well, there would be something like CV plus DW plus EU. This is what linear combinations will look like. Now, the question that is interesting here is when we are given three vectors in three-dimensional space, what is the space of all linear combinations? Or rather, what can the space of all linear combinations be? Well, if all three vectors are the zero vector, then the linear combinations, no matter your choice of C, D, and E, would again be the zero vector. So one possibility is the origin, which now will have three components because we're in three space. What is another possibility? So another possibility could be that all three vectors look very similar to each other, or are multiples of each other. So for example, you could have V to be 1, 2, 3, then W could be 2, 4, 6, and U could be 3, 6, 9, for example. So this is an example of what we could get. Well, then any linear combination would be a multiple of V. Why is that? Well, we see here that W is in fact 2V and U is in fact 3V. So when we look at a linear combination, CV plus DW plus EU, what we get is C times V plus D times, now instead of W, I can write 2V. And then plus E, instead of U, I'm going to write 3V. So what I see here is that I have V, 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 and the rest are just numbers. So obviously D times 2 is 2D, E times 3 is 3E. I can factor V. So what I will get is C plus 2D plus 3E times V. Now, this expression is just a number that is multiplying V. So since W and U are multiples of V, then their combinations will also be multiples of V. Geometrically speaking, I don't want to draw too much in 3D space because that's not an easy thing to do, but just to give you a picture, it looks like this. You have some vector V, let's say this is the vector V, then W would be twice V, and U would be 3 times V. Then just like in the 2D case, no matter how you combine these three vectors, you're always going to stay on the line that passes through V. So it is possible to get a line, even though you have three vectors. And the reason we got a line was that, in fact, the three vectors already laid on the same line. Now, what's another possibility? The other possibility is that we get a plane. So for example, if V is 1, 2, 3, W is 1, 0, 0, and U is 2, 0, 0. What we see here is that these two vectors are essentially the same. In what sense are they the same? They're the same in the sense that they are on the same line. They describe the same line, the line that is in fact the x-axis. So they're both on the x-axis. They don't have y components. They don't have z components. But the vector v is not on that same line. So this vector v is on a different line. So if we were to look at this as a picture in 3D space, it would look something like this. It's not a precise representation, of course, but you get the idea. So let's say I have my v here, and w is going to be along the x-axis, which I'll choose to be this one. So it's right here, and u is right there. So you see that as vectors, they don't really give much. Then what you get as a combination is a two-dimensional space, regardless of the fact. So it would be the plane through the origin that contains these vectors. So now we get a plane through the origin. So here, when I said a line above, I should say a line through the origin. That's very important. Because remember, we can always choose the coefficients or the scalar c, d, and e to be 0. And the final case is when all three vectors are in different directions. So for example, the vector v is 1, 2, 3, and then I'll choose something easy for w. It could be 1, 0, 0, and u could be 1, 2, 0. So you see that all three vectors are in different directions, and therefore their linear combinations, so CV plus DW plus EU, describe the whole or the entire 3D space. So what is the key question that we have to think about? We have to think about whether or not these vectors are multiples of each other. We can talk about these things in higher dimensions as well. Addition and scalar multiplication is defined for an arbitrary number of vectors. So I'll just write that briefly. If you have a vector v with components v1, v2, all the way to vn, and a vector w with components w1, w2, all the way to wn, you can add these two vectors you can look at their linear combinations, cv plus dw, and they will be component-wise, cv1 plus dw1, cv2 plus dw2, all the way to cvn plus dwn. The reason we spend a lot of time with two-dimensional and three-dimensional vectors is that we do have the geometrical representation. When you go to higher dimensions, the geometrical representations are not really our thing to come up with them. We can't really visualize anything beyond 3D space. But the same intuitions work in higher dimensions, and that is the key. All right, we will go into the next topic of vectors, which is going to be scalar the dot product and the length of a vector. But with that, I'll give you another video. Right after this video, you have some examples that I would like you to do, just in order to test your knowledge, to test your understanding of what we've talked about so far. And once you do those examples, you will have the confidence that you have understood this section.